Hello, everyone. Thank you very much for being here today. As said, my name is Mariana Avezum, and a few months ago, last September, August, around that, Diana and I started a group at the Technical University of Munich to build a Hyperloop pod. General question here, how many of you have ever heard the word Hyperloop or know what it means? I love that. that makes me happy. Before I start, a short video about our project, which was just released this week.
The Hyperloop concept is an amazing concept because just imagine getting from Munich to Berlin just within 35 minutes and in a really green and sustainable way, as we are not emitting any CO2. This is the future of mobility.
The Hyperloop is a train that can go really fast. The two main reasons why it can go so fast is because it's operating in a closed tube with no air inside of it. So we don't have aerodynamic drag, and because we're not running on a track like a normal train is with wheels, we also don't have friction from the wheels on the track.
My institute is highly proud of that. This is one of the very few groups, namely 30 out of 700, which applied for the project. So only 30 are in the last group.
The special thing about our team is the compressor. The compressor makes the whole pod scalable. So Elon Musk can take our pod, scale it up, including the compressor, and has his own Hyperloop.
We are a team of 37 students who are super motivated and ambitious to win this competition. Every one of us is working super hard next to our studies.
The Hyperloop is a very perfect project to learn to design things. And this in itself is so important. So this will have an impact of engineering in the future.
We want you to get on board and join our Hyperloop ride. We want you to share the same vision as us. The same vision as Elon Musk for a more greener and more sustainable future of transportation. We want to tackle the issues of global warming, of traffic and pollution. And this has to start now, and we can only do this by innovating, disrupting the current mobility system.
I not only think this is a very good idea, I'm convinced that they will win the competition. I'm crossing my fingers that they will succeed.
So yeah, Walter is probably right. We'll probably win the competition anyway. But yeah, just a short introduction. So what is the Hyperloop? Whenever I tell somebody that in the future you will travel from Munich to Berlin in half an hour, the first reaction I always get is that everybody thinks I'm talking about science fiction and this will never happen. I'm here to tell you today that the Hyperloop is much more feasible than any of you ever probably imagine, especially because most of the technology behind it is actually things that already exist today. And basically what the Hyperloop does is get one piece of technology from each application and copy and paste it and combine them together in its own environment. So for you to have an idea how little different things there is in the Hyperloop. We are building a Hyperloop pod and have not come up with one patent or one research topic that we can register on that, because all of these things actually already exist by themselves. It's just the way of combining them actually builds the Hyperloop. The idea was suggested in a 60-page alpha study by Elon Musk back in 2013. And when Musk originally announced the idea, two independent companies, which basically were people that used to work for Musk and stopped working for Musk to start their own Hyperloop companies, formed. Today they are known as Hyperloop Transportation Technologies and Hyperloop One. They actually went to build a full-scale Hyperloop that will connect Los Angeles to San Francisco, Bratislava to Wien, Munich to Berlin. There are many, many, many tracks that are currently under study. The idea behind the entire system is that capsules speed through low-pressure tubes. The low pressure is very, very important. Vacuum tubes that have capsules speeding around them have been around since the late 1800s. Banks have been using them to send letters around a few generations above us. That's really nothing new. Why did no one ever come up with the idea to scale that? The problem behind that is that when you scale up a vacuum, infrastructure costs really easily go up really high. And that's the whole innovation of the Hyperloop. The Hyperloop does not work with vacuum. It's around 1% of the atmosphere temperature, atmosphere pressure, so like 1% of the pressure that we currently have now, which is actually a lot of air. This allows for the infrastructure costs to be around 6% of the infrastructure costs of the maglev, or the Transrapid. Every time I talk about the Hyperloop, people say it's not going to work because if the Transrapid didn't work, the Hyperloop won't. The infrastructure costs are only 6% of the Transrapid costs that were projected back then. Okay, so you have a low-pressure tube, and inside you put pods that levitate. By levitating, you'd remove friction. By having low pressure, you already greatly reduce air drag. But in order to completely remove the air drag that you would still have inside because of the remaining air in the tube, you put a compressor up in the front. And this is how our prototype currently looks like. This is the prototype that we are currently building in Garching. If you are ever in the makerspace in Garching, you might have seen parts of it. I know it's a bit counterintuitive, which is why I'm going to say it now. It goes in this direction. So this is the front, and this is the back. And yes, the guy is traveling backward. And if you don't think that's comfortable, it's actually safer for the human body when you are braking. That's true. That's true. That's really true. Didn't make that up. So yeah, the compressor is a key feature of the Hyperloop. And I'm going to get a bit more into detail about it later. But now just an overview. What it does is that it basically sucks in the remaining air in the tube and acts as a big vacuum cleaner, sucks the air in the front, passes through this air duct, and expels it out in the back. And there's an outlet in the back that you can't see from this angle. The Hyperloop also, our prototype currently contains the 6 subsystems, very important compressor. Then, of course, we have, and the compressor is operated by an electric motor, because one of the key motivations about the Hyperloop is to build a green transportation concept. That electric motor is operated by an onboard battery. We are trying to build a battery that has that awesome Tesla feature where you can slide it in and out and just very easily have a backup battery. Of course, anything that speeds up to 1,200 kilometers per hour needs to have a hell of a braking system. And therefore, we don't have one braking system, but we have 2 of them. Diana will go a bit more into detail about that later. The friction and eddy current brakes, one for high speed and one for the final part. I already mentioned another key concept of the Hyperloop is the levitation. And before everybody kills me for having these wheels in there, I know they are not as beautiful as just a levitating pod. But there are very good reasons for having wheels. There is a very good reason why wheels were one of the first inventions of humankind. They react beautifully up to actually quite decent speeds. And then for the high speeds, when they can't handle it anymore, then we levitate. So our current concept is to have a Hyperloop similar to an airplane. You have wheels in the beginning and the end when you are not at extremely high speeds, and then after you reach a certain threshold, you levitate. More on that and how that works later. Of course, no, I should have, yeah. The structure is a lightweight structure. We try to keep it as modular as possible in order to be able to integrate all the systems on that. And the brain behind this whole thing, I'm sure there are many computer scientists in this room, is a very fast and computer that Diana is also going to go a bit into detail later. Another question that always comes up when I show this picture is why only one person? Well, why only one person? The answer is a competition. We are not building a full-scale Hyperloop. We are building a prototype. And the second question that comes up is, what is the scale of your prototype? And the answer to that is a bit more complicated. Because when you're building the technology that we're building, the compressor, the brakes, even the levitation system, most of those things are quite easily to scale. They just, as long as you maintain the same tube-to-pod ratio, those things are just really just make the pod longer, and that's OK. And making the pod longer is basically a design problem and not engineering problem, which is why we don't really focus. Design, I will totally agree with you. We do not have the most beautiful pod in the competition. But we do have one of the most scalables and one of the technically best, in my modest opinion. So Elon Musk announced in last July the student competition through his company SpaceX. Originally, over 700 teams were registered in the competition. And yeah, when I saw the announcement in my Facebook feed sometime in July, I said, that's a hell of a project. That sounds like something we could start. And then the story goes that I called her at 12 in the evening or something, and the girl didn't sleep all night. Until we landed in our current stage, we have gone through several iterations. If you consider that this project started in August, and we are now in June, and are actually 30 days away from construction finished, from end of construction, you have the idea, you can maybe start to have an idea of the timeline of this whole thing. In November, we only had a very rough proof of concept, and back then we had defined the subsystems we wanted to use. Back then we had already decided that we wanted to keep the compressor. And with the design, the first design that you see on the right side, we were accepted into the design weekend in Texas, which took place in January. Then we had time until January to update and make our concept a bit more mature. And in January, we presented that pod over there, the one in the middle. And it was a very cool event in Texas. We got to see Elon Musk and watch the keynote directly from him. I was sitting in the second row. And the concept that you see in the middle is the concept which passed us, and the concept which took us into the final round. One of the main reasons for that to happen certainly is the compressor. That is one of the things that we have that most other teams in the competition do not have due to its complexity, which really isn't small. But I'll go more into detail about that later. This is the amazing team that made it happen. That team picture is, for once, actually quite updated. It was taken, 2-3 weeks ago. If you imagine from the original 7-people team that came up with the first design in November to the 10, 12 people that worked on the January design, things scale up quite quickly, and the Hyperloop project has escalated and taken proportions that I would never have imagined when it all started. And of course, that is only possible because of the awesome team. But yeah, how do all of these subsystems interact with each other, and how do they all take place? I'm going to go through the talk and tell you a few of the stories and problems that we had on the construction process, and try to take you through a few of the iterations that we had. So, as I said, the Hyperloop was originally proposed in an alpha study by Elon Musk back in 2013. In that alpha study, Musk suggests air bearings as a levitation system. Air bearings, you can imagine them as working very similar to air hockey tables. Basically flip that around so that the air comes from the top and not from the bottom, but it's the same thing. And here you can see that image I actually took from the alpha study itself. And the cool thing about the air bearings is that they can handle a very heavy load and have very low friction. Since you have this air tissue between the pod and the tube, it removes the friction, and you can still keep very heavy load. The other cool thing about air bearings is that in a full-scale Hyperloop, you have a huge compressor in the front, sucking in all that air. What do you do with all that air? It's you throw it to the back, but if you compress that air at a high enough pressure ratio, you can actually use the air that you get from the front and use them for the air bearings. If you connect the air bearings to the tube, to the air duct that I showed you earlier, this is how that would work. And it's a very cool concept, but it has some problems with it if you think about it actually constructing and putting it in production. One of the biggest problems is that the hover height, so the height at which you would levitate using this concept, is like micrometers, which really isn't the safest thing on the planet, let's put it like that. From the beginning on, we said we wanted to build a prototype that was safe and scalable. And there were two very good reasons for not going with air bearings in our design. One of them was, of course, the safety issues related with micrometer hover height. And the second of them was that the air bearings could actually work nicely in a full scale, but we're not building a full scale, and therefore the compressor that we have in our prototype cannot achieve the pressure ratios necessary for this to make sense. That means that we would have to carry on pressurized air on board in order to have an air bearing, which means a lot of extra complexity, extra weight, and weight means less speed, and weight is always something that you should try to avoid. For those reasons, we actually ruled out air bearings quite early on. A few of our first, we looked into it, of course we looked into it because it was the concept explained in the alpha study. But in a quite early stage in the competition, we actually decided to try to go with these rotational magnetic hover engines. And the way you can imagine this is you have a magnetic, there's actually a very awesome YouTube video. You can Google SpaceX hover engine, whoever wants to watch it. The guys actually created a hoverboard that actually levitates. They are discs about this size and big magnets that have a motor in the middle of them and therefore rotate. By rotating, you then create a magnetic field that allows you to levitate. There's a company producing that. They are called SpaceX. And from a very early age on, they announced that they were supporting the Hyperloop competition. And since they were supporting the Hyperloop competition and they had this amazing technology and they were producing it for us, that was a lot of work that would get removed off of our hands. So we actually, for a very long time, considered using the SpaceX. The idea is brilliant, and it has some very interesting additional benefits, such as you can levitate it since the discs are rotating, since the hover engines are rotating, you can levitate your pod even if the pod is statically stopped, even if the pod isn't moving, which is something very useful for testing. If you can levitate it anywhere, it makes testing quite easier. And of course, it's just cool. Everybody wanted to do the hover engine, the hoverboard test with it when we are talking about using the SpaceX. But as things evolved, we started to realize many non-expected problems with the SpaceX. A non-very small one of them, which actually was half expected, was their price. At a price of, back then, they were $5,000 per engine, and we needed 16 engines to levitate our entire weight because we had a lot of weight because of the compressor. You can do the math yourself, how much that would have cost. And we really weren't that rich. So yeah, that was one of the reasons why we started looking into another levitation systems, but to be honest, it wasn't even the biggest of them. What we eventually realized is that at high speeds, the SpaceX were just very expensive permanent magnets. Because in the beginning, you have this awesome feature that you can levitate standing. The Hyperloop isn't meant to stand. The Hyperloop is meant to go fast. And when you're going fast, you can get the levitation effect even without rotating because you have the difference between the difference in speed between the pod and the tube. You can achieve that with a permanent magnet. And they needed to be lubricated, which presented a cooling problem, and they needed to be pressurized, which increased complexity, and. We eventually decided to remove the SpaceX, which was a decision that was probably one of the biggest and hardest decisions in our team because it was very contradictional. Some people didn't want to have, some people just thought, we have this system, it works, we'll find the money somehow. And other people were like, we can do so much better than that. Can we do so much better than that? And can we do so much better than that in a few months' time, which is always the timeline in the Hyperloop? Our current concept, you might remember my rendering earlier. We introduced the wheels. Wheels are very contradictional because they are not part of the original alpha study Hyperloop. They make the pod look ugly. We lost 1,000 sexy points the day we added those wheels. It's true. Everybody. The cool thing is that it levitates, and the second people see a wheel, oh, it's just a car. It's not a car. It's a Hyperloop. But the wheels make it look like a car. So yeah. FYI, the wheels are only necessary in the beginning and in the end. In the middle, we have permanent magnets. And we went through several iterations of designing these permanent magnets and seeing which type of magnets have the necessary force to levitate, to have this to have this magnetic effect on the tube. So the floor of the tube is made out of aluminum. And then there are 1,000 different types of magnets that you can actually see how we levitate best against this aluminum. Wheels are very easy. You can basically get them in 1,000 different wheel producers out there. Wheels that can take the currently 600 kilograms of the pod are a bit less easier to find, but even those are present in a few systems. To be honest, today the wheels that we have inside of our system are wheels usually found in roller coasters. Going back to what I said earlier, that we copy-paste systems from different things and build a Hyperloop, that's one example. The permanent magnets, of course, have the huge advantage that they are cheaper. If we design a nice casing, we can actually just, we need to design the casing and how to sustain them into the pod that we designed ourselves. But the rest is quite easy to build in-house. The magnets do have one very big problem, which is transportation. We're building this thing in Garching, and the competition is taking place in Los Angeles. How do you move this from one place to the other? We don't have time to wait for a ship to go over. We really don't have 1 month time to lose in transportation, so this thing has to fly. Airline companies do not like having big magnets on board, not even, yeah. They really don't. Even if it's cargo, even in cargo airplanes, they simply say cannot. Just pure cannot. So yeah, those are a few of the problems that you never think you'd run into. The solution to the transportation of the magnet problems is actually finding a supplier. As I said, the advantage of them is that they are cheap. So we actually bought them twice and had them once delivered to Germany, where we build them into the pod, test, make sure that it integrates and everything works, remove it, ship it without the magnets, and have the exact same magnets delivered to Los Angeles and build them over there. That took us a while to find a supplier that did that, because basically it's delegating the transportation problem to the supplier instead of us, but it worked. But yeah, so we removed the air bearings and came up with our own levitation system, but in the original alpha study, by the way, that image is from the alpha study. It's one of the most famous Hyperloop images there are, even if nobody ever understands what the Hyperloop is from that. But yeah, one of the reasons for the compressor was to generate the air for the air bearings. If we don't have air bearings, do we still need the compressor? And yes, you do. Even if most of the teams in the competition do not agree with me, and even if really a very, very high percentage of the teams in the competition decided to remove the compressor, it is essential for the Hyperloop concept. It is the only thing that makes the Hyperloop work. And this is, I'm going to go into a bit more of detail here, because it's one of the reasons why that makes us different from most of the other teams. And it's also one of the reasons why the Hyperloop is the Hyperloop. The thing that is important to understand here is that our test track is only 1.5 kilometers long. So you really don't have the amount of air or time or length to actually have the accumulated air in front of the pod. The whole idea behind the compressor, if any of you have ever used a syringe, is that if you have a syringe and you want to press it down, it's going to get harder and harder however much more you press, because the air in front of it is getting compressed into the smaller space. Since we don't have a 600-kilometer test track from Munich to Berlin, we don't have that. The space is not critical, and you could compress the air into that. The amount of air could still get compressed. And so many, many, many teams in the competition, and to be honest, all the teams that I know of, removed the compressor. basically because you actually don't need it for the competition if you design your pod in completely different ways. The compressor is very heavy. Only our complete system is 600 kilos, and only the compressor is responsible for around 200 of that. And the complexity of developing and testing something like that is companies usually take years to come up with a compressor. We had a few months, which also is not easy. But the thing of it is, a Hyperloop without a compressor isn't a Hyperloop. I am so sorry, MIT, but if you do a 90, MIT's pod fits a human being that is 90 centimeters big. How many 90 centimeter big human beings do any of you guys know? Therefore, their pod is very small. Therefore, they are very light. They do not have a compressor. I am so sorry, but for me, that is a levitating shoebox. So yeah, in a very early stage, we had the whole keep or not the compressor. And the reason to keep it is that it is essential to scaling up. The compressor is the one thing that is actually new in the Hyperloop concept, that is different from the Transrapid, that is different from the Swiss Metro, that is different from the bank tubes that were sending letters up and down. Those things operated at vacuum. The only reason the Hyperloop does not operate at vacuum is the compressor. Sorry for the big text, but that's a quote from the Alpha study. I'm going to read it to you. Wherever you have a capsule or pod moving at high speeds through a tube containing air, there is a minimum tube-to-pod area ratio below which you will choke the flow. What this means is that if the walls of the tube and the capsule are too close together, the capsule will behave like a syringe and eventually be forced to push the entire column of air in front of it. Not good. That's what the compressor does. It gets that entire column of air and eliminates it so that you can have the airflow through the pod. By the way, we stuck so much with the compressor that is a picture of our Werkstatt, and that is our compressor. You're going to tell me that's a small compressor? Yeah, I know. The reason for that being a small compressor is that we actually went for the big compressor at some point. Our November design had a beautiful, light, practical compressor that was using pressure ratios per stage of things that you'd find in modern, actually being developed today by General Electric or MTU. Very cool, very beautiful, scientifically awesome, probably perfect for the Hyperloop, but not really for students who need to build it, test it, and ship it to LA in 4 months without a budget. So we started going into options of things that we could at least in theory build. The second image over there is the compressor that we presented in Texas. It had 12 stages in the compression ratio of 9. For those of you who don't understand compressor, this is basically made up of stators and rotors. And when I say compressor, what most people think is airplane turbo engine. And it's not completely wrong, it's just not complete. The thing of it is that airplane engines do have compressors inside of them, and that compressor was actually modeled after the Starfighter engine. The thing of it is that after a compressor, an airplane engine also has a combustion compartment to propel. The compressor in the Hyperloop is not responsible for propulsion. The compressor in the Hyperloop is just responsible for drag reduction, for minimizing this amount of air in front of the pod. So we don't need big combustion explosions taking place. The propulsion comes from outside through the tube in linear motors. That compressor was beautiful. We designed it ourselves. We really designed that compressor in 1 month. And for you to have an idea, General Electric, when they're developing something like this, and they do, this is what they actually do for business, and we came into contact with them, they usually take 5 years to design that. We didn't have 5 years. So we built it as far as we could. We designed it as far as we could based on studies and simulations that we're doing. and presented it in January, being a bit arrogant and assuming that we could pay the 530,000 euros that thing costed. Only the compressor was weighing 600 kilograms, which gave us an entire pod weight of around 900 kilos, which is simply way too much. So yeah, that compressor was beautiful in theory and probably would still be the perfect compressor for a full-scale Hyperloop, which is why we passed. I'm convinced to this day that one of the reasons that we passed into the final stage is that compressor, and it is the arrogance that we had in saying that we could actually pay for it. That is a photo of the trophy that we got when we passed in January, signed by Elon Musk himself. We are very proud of Elon Musk's signature. The piece of metal you see in the middle is actually a sample of the iron Stahl that is going to be used to build the actual tube. And it's sitting at our office in Garchingland. But yeah, we had a beautiful compressor that we totally could not test and build in 5 months, or 4 months, 3 months. So we had to actually redesign. We had stood so much for the compressor and we had sold it so often that at this stage we couldn't remove it. It was the entire reason why we were as far as we would. So we eventually came up with the approach that having a compressor was better than having no compressor at all. We didn't have time to produce and test our own compressor, neither the time, nor the money, nor the knowledge. So the best thing we could come up with was buy one off. After countless phone calls and going from faculty to MTU to everyone you can probably think of that is into the engine business, we were able to find an old Alpha Jet engine compressor laying around. Yes, yes, and it had basically been laying around and not being touched for like 20 years. So yeah, 20-year-old technology. It's not the beautiful compression ratio of 9 of the other one. This has a compression ratio of 1.6, 1.7, I think. So yeah, it's not the perfect compressor for the Hyperloop, but it is what we could get in our limited budget and time frame. If I go back here, this is actually the compressor. This picture is actually the compressor, how we bought it from our supplier. And here you can actually see the blades, and you can actually move them individually, maybe remember from the video. And what we did is, this thing is usually connected into an airplane engine and connected to the combustion and blah, blah, blah. That's not what we need. So we had this external part here manufactured for us by awesome sponsor that gave us to us for free. And modified the compressor that we bought to in the housing and then able to connect it to our electric motor and fit our requirements. And that was the best plan we could come up with at the time. And actually, the compressor was, we had so much work in the compressor that, ironically enough, it was the first thing we ever bought. Things that the one thing that most teams don't even had, it was lying around at our workshop for weeks before anything else came into, because most of the other things had a very long time of production and delivery. So this is when we started going into where would we store all of this? How would we pay for this whole thing? How could the 12 people that built that awesome design in January actually build a Hyperloop? Building a design is one thing, actually constructing a pod is a whole other story, which is when we started to scale up our team. In our first week back, we had a recruiting event. That's a picture of the recruiting event, and me trying to recruit motivated students to join the team. In one day, like 12 different people joined the team. We had free beer because nothing gets students to go as free beer. And yeah, nothing like people and motivated students to actually build a pod that has so many changing requirements always and always. And one of the systems that suffered the most with changing requirements was the braking system, which Diana now gets to talk a bit more about. You can go.
So I will speed a little bit up because, as usual, it's a lot of information, so we can't stop in the right time. So actually, the initial... Is it working now? Yeah. Sorry. Yeah, so the initial plan was to have friction braking only, which is actually the pneumatic system. So as you can see right here, there is a pressure tank. So we actually use the scuba diving tank to put a lot of pressured air inside. And then it's actually controlled by 5 valves here, pressure valves. And for the initial state of the brakes, they are deployed. That was for our safety, because in case something goes wrong, computers don't work or some cabling doesn't work, the worst case for us is just stopping the pod. So we will not crash the tube, because it's actually really coming requirement from SpaceX. So whenever we want to release the brake, we just can configure this valve. So we open it for some time until the pressure comes to the brakes. Then these springs, as the pressure comes from both sides, the springs get released, and then you can have the released brakes. And except that, we also have a redundant brakes. So in case something goes wrong and the main braking system is not working, the secondary one is still able to stop the pod till 0 kilometers per hour. So we will have no problems with stopping the pods in any case. But actually, the bad thing is that requirements are changing really, really fast. And actually, one of the guys asked in a design weekend, especially to Elon Musk, why the requirements are changing so frequently. And he actually told, it's also kind of challenge, and you need to accept it. And yeah, we did. So here we just decided to add eddy current brakes, because they just told that high-speed friction braking is not allowed anymore because we can damage the rail. So we should have come up with other intermediate braking till we can use our actually friction brakes. And here where it comes eddy current brakes, I will explain you a little bit later how it's working. And the problem with eddy current brakes was that we really had no experience with that. And we didn't know how to test it, because actually simulating is really hard problem. And the solution for that was to just hire new people to the team, and also have great sponsors who advised us a lot and actually helped us with simulating all the stuff. And that helped really us a lot, and now we have already a structure how we can have our eddy currents working. And here, so it's the image, the CAD model of our eddy current brakes. So the brown ones are actually the copper wires, and these gray things are iron, just pure iron. So whenever we power up the eddy current brakes, so it's not powered out in the beginning. It's actually even using the same battery pack as for compressor. So we just, whenever we start the eddy current brakes, we need to power off the compressor. So it's actually the energy going from compressor to the eddy current brakes. And then we power up the coils here, the wires here, sorry. And then it actually, these pairs, just in front of each other, they make opposing magnetic fields. And because of that, actually, the kinetic energy gets transformed to heat, and it actually stops the pod. And the current is flowing inside of the rail here in the middle. And we can actually stop the pod, but it's really not a good idea to only use eddy current brakes for stopping till 0 kilometers per hour, because in the beginning, in high speeds, it's really efficient, but then it becomes worse when you are having less speed. So that's why we actually use it till 10 meters per second, and then we switch to friction brakings. And in that case, we will not damage the rail, and we will be even fast enough to stop when we need it. So actually, everything, this is not only mechanical, so actually it needs to be controlled by computers, of course. And here it's I know it's a little bit small, but it was really huge, so I couldn't make it smaller. It's actually all the workflow we need to go to control all this stuff. And even we need to have like external, so remote control, because whenever the pod is inside of the tube, we have no access to it. So we can't push any button, we can't have access to the computers inside. So that's why we also have a remote control. So we have a user interface where we can start the compressor, launch the hub motor to ride till the end. And actually all these things are also included in computer systems. So we have it, we need to have it implemented by like at the end of the month. And computer system actually really also changed a lot during the time, because at the beginning we just thought, okay, we need a redundant system, we need fault tolerant system because it's really important for safety. But then we just realized it's really not possible by the time frame we have. So we tried to keep the architecture as simple as possible, but still to have safety in crucial things. And here where it's coming from, so this microcontroller is actually responsible for all critical stuff. So if even the CAN bus, which we are using for connecting all microcontrollers, fails, this controller can still stop the pod and ride till the end of the tube. So that's what we actually want to reach. And even here, this redundant connection is straight to high voltage battery, because for switching to eddy current brakes, we need to tell the energy pack here to switch the energy from compressor to the eddy current brakes. So to be able also to do it in case of connection failure, we also have this redundant cabling going straight from the control microcontroller to energy supply. So in this case, we really made redundant all crucial things we need. And here the other microcontrollers are actually, this one is responsible for telemetry. So we need also to get all sensor data out of the pod so we can see it on the screen, and actually also send the commands to the pod, like compressor power on, power off. So this microcontroller is responsible for that one. And actually, this is not real time, because we don't need a real time system for getting all the data out, because we can just also, we are writing on the SD card, and then we can also look it later. And energy supplies, we have like here 2 microcontrollers, because actually we wanted to put them inside of the energy pack so that they're totally replaceable in case something goes wrong, so we can just like plug it out and plug it in back the other one, and then we will be safe with the competition. And the other one, which is actually responsible for compressor, it's already coming from the industry partner, so we are not developing it, we have it ready already. So mainly we also have like redundancy in sensors. So here, for example, IMU and speed sensors. So this is the rotational speed sensor, which is counting the rotations of the main wheel, from where we can get the acceleration of the pod, so the speed of our pod. And IMU is actually also have accelerometer inside. So we tried to keep also sensors as redundant as possible so that we can know which one is actually right, because maybe some sensors will not work. Actually, in vacuum, it's quite hard. So we need also to test that how sensors behave themselves in that environment. And all of this, of course, needs to go to the structure, which needs to be light, because we already have a compressor which is really heavy, and we wanted to make it as light as possible because the levitation needs to be able to hold it up. And for that, we use a carbon fiber hull, which is expensive but really light, and it meets our all requirements. We also have the lateral stability guided wheels, which is actually which is actually touching the rails from the sides, so that whenever we start levitating, we have a stability, because otherwise we couldn't do that. Because only with permanent magnets you cannot handle the stability there. So for now we actually come up to really how we can test it, because it was really hard. We don't have access to the tube until we don't go to Los Angeles. But whenever we reach there, it's really too late to change something if it's not working. So we came up with several ideas how we can test it. So first one is just we will make a test bench for braking, and we need to actually here, this is the friction brakes, so we need to know how much power we need to put into rails so that we stop, but we still don't damage it, and we need to know the distance of brakes and also the time which will take. And the other one is also eddy current brakes, which also needs to be tested about the speed and also the heat, because actually eddy current brakes produce a lot of heat, and we also have problem of heat there because it's almost vacuum there. And the guided wheels actually needs to be tested because they are really small, so the speed of the wheels like rotating, it's really high. So we need to be sure that they will resist that speed, and for that we need just to test it in the test bench. And the other type of the test we came up with is actually the vacuum test. So we have vacuum chambers, and we need to test mostly electronical stuff because we don't have a lot of air inside like we have here. And actually that air maybe is not enough to take heat out. So we need to try to keep everything really simple so that we don't use a lot of electronic stuff which is producing a lot of heat, because we cannot handle it in that case. So actually the whole system will be tested at the end of June, and we will even put compressor there so all the system will work, and we will see how the heat is handling there. So the first vacuum test was done already with one microcontroller. So this is the actual image from the vacuum chamber we had. And it was really good because it's only using 3 volt of power. So we really was amazed with the test. So we had really no problems with microcontrollers. And next test is going to be actually in the next week. So next week, Tuesday, we will do it. And it's going to have already the connection, so CAN connections between them, and also some sensors connected to them so that we can also see if sensors are working, how they are behaving in that environment, and how actually precise are their values. And yes, as you can see, all of this is really crazy idea, and this is new technology. And we found like a really one part which is really fitting our way of thinking, which is like 2 roads diverge in a wood, and I took the one less traveled by, and that has made all the difference. And yeah, we did it. We went to the hard way, but we actually really happy to make it happen, and we already see the results coming out. Thank you very much. And if you want to know further news from us, then you can just like our Facebook page, which is VAR Hyperloop team. And also, if you want to support us, we have an Indiegogo page, so you can just sponsor some money if you want. Thank you very much.
The pod is 4 meters long, and sorry. Oh, and I am the button.
Yeah. So actually, the answer was just the question. The question was: so you want to know the distance or the time? Which time? Okay. So actually, the distance is so the question was: what is the time where we will be inside of the tube? So the question is only really like the ride will be only 2 minutes, and there will be some testing when we are in the staging area. So it's in the beginning when you enter the tube. it's still not like the right, but they want to test also some stuff. For example, like if the hub motor is working, if the linear motor, which is launching the wheels are working, so they need to do some testing. So most probably we will be there like around 10 minutes overall. Yeah, but they didn't specify it yet, like what tests do they want to do and all that stuff. But we assume that they need to like try it before, because they need to be sure that we will not break the tube.
But I didn't quite get what happens if like your battery breaks. You don't have any power supply anymore. Are you like stuck in the center of the track, or do you just continue and at some point the brakes hit in? I mean, you can basically use the Eddy current brakes only when you have power. Are you like in emergency still using the other brakes, or do you use air for braking because the capacity is
Okay, so as Diana explained earlier, as the second the battery goes out, the second the energy is lost, the friction brakes will automatically kick in.
You have it.
Yeah, I did. Okay, repeating the question was what happens in an emergency situation if there is no energy, and how do you maneuver the pod outside from the tube? And the answer to that is the second the battery goes out, the second we lose energy, because of the pneumatic design of the friction brakes will automatically kick in and stop the pod. So that's the first thing to handle, is to stop the pod so that it's not traveling at I don't know which speed uncontrolled. So yeah, friction braking for emergency braking, it's not ideal, but this is an emergency situation, so that's okay. Would probably damage the tube a bit, but and how do you remove it from the tube? This is this part of the design here. Maybe you can't understand it too well because it actually goes inside, but we have a system called low-speed maneuvering system, which is really, really, really low speed. You are not supposed to travel the tube with it, but you can. This is exactly the situation where the low speed comes in. They are retractable hub motors, so retractable wheels that have hub motors inside of them, and they will go down, and then you slowly go up.
And do you have any collision avoidance? Like, I guess there would be a lot of traffic in these tubes, and if you break down, you don't have power, you can't tell anybody that you're...
That goes back to the computer intelligence. That is the responsibility of each pod to look and watch what is happening in front of you for their own and activate their emergency brakes if necessary. So yeah, you can have a camera just looking in front that will be fast enough and activate the brakes.
Yeah, so actually for the competition we didn't do that because it's not in requirement. So we will be like alone, and it's just like straight tube going. So actually there is nothing which can come up in the front, and just because of time problems we just did skip it. But it's not a problem. Yeah, you can do it like we even thought to put a laser or the camera in front. Just then we removed it because of time constraints.
Yes?
Question? Yes, over there. Is it designed to go only straight, or it can also maybe turn?
The question was how does it handle turns? So yes, the Hyperloop is designed to go as straight as ever possible. It does not react very well to curves. Even you need huge curve radius to even start thinking. When I say huge, we're talking like 100 kilometers big radius for a curve, because you don't want to do a curve going at this 1,000 to 100 kilometers per hour. So yeah, the idea is you can make a curve to go, for instance, outside of the city. When you're going out of the city, you can't connect city center to city center in a straight line. And the idea is you make a curve and go at low speeds, get out of the city, and as soon as you get out of the city, you start accelerating, and then you have a straight line into the other station.
All in the back, please.
I was having the same question, but now given your answer, I think your actual problem is that you need a lot of digging technology for tunnels. Cities are of different heights, and is there any idea how you solve that problem?
Yeah, so the question was how actually the tubes are going to be made, because the cities are like in different heights, so you need to handle it somehow. So the answer is that actually we are designing only the capsule, but just from our guess, I mean from which we already had some research on it. Actually, it's going to be over 6 meters above the ground. So it will not, because whenever it's in the closed thing, so if you need to dig the mountain, then you have pressure problems there. So it's best if it's over the ground. So I think even if you have different heights, they will just put it like this, but not dig it inside, also, or maybe only short parts.
Also, one way that you can correct it, of course, is the tube is so the tube is not underground. The tube is overground in order to reduce construction and infrastructure costs. Oh, sorry. And these pillars that sustain the tube, you can actually make them different heights to correct terrain height differences, for instance. So it's not a problem if one pillar is a bit taller than the other one, as long as the tube that they connect stay at the same height. Then the pods will stay at the same height. Mixture of both. How much automotive technology and how much aerospace technology is involved in this? And the answer really is a bit of both. So Diana was mentioning earlier, this thing is autonomous. There's no pilot, no driver, or whatever Hyperloop operating person would be called. This whole thing is autonomous, but it's not the same type of autonomy that people usually think when we're talking about autonomous cars. Autonomous cars are usually related with detecting street signs and pedestrians and all of that. The biggest advantage of the Hyperloop is that it's a totally controlled environment. You have the tube and the pressure exactly at the, you have the pressure in the tube exactly where you want it. It's also quite resistant against weather changes. So it doesn't matter if it's raining, snowy, freezing, the tube is the tube. Everything is closed and nothing is going to freeze the pod in there. So yeah, as far as pressure is concerned, it's certainly more aerospace. As far as recognition and sensoring is concerned, that is definitely something that we get a lot from the automotive industry. This thing has loads of sensors all over it. A bit of both, depending on which aspect you're looking at.
So one final question.
What will be your next milestones you will be working on? Or,
In 31 days will be our construction. In 31 days, our construction needs to be done. We have a rollout event in Garching, and hopefully by then the entire construction will be done and initial testing will be done. So right now we're looking at a competition date of around August. SpaceX hasn't announced it, so we don't know exactly when it is, because it's SpaceX. But we calculate with August at some point, which means that half of July we need to ship it over to LA, which gives us June and part of July for finalizing and testing. So yeah, construction ends in 31 days. I have no idea how realistic that is. But it's okay, it's okay. We're a bit late in the schedule, but we'll make it.
Okay, so are there any questions beyond? I guess the speakers will be around for some time, for the whole day, or how long will they be around?
At least until lunch.
At least until lunch. Yeah. So let's, for the moment, let's thank them again.